Let's take a second and recap the things that has led to this point. So let's close our eyes. So we started the chapter by classifying materials based on what? Based on time. So when you have a force acting on an object or a material, if it's time independent, that is, the effect is time independent, then they are solid. If it's not, then it's liquid or fluid. Now, we went on to fluid, and in fluid, we study fluid by classifying them as stationary and in motion. So when it came to stationary, we looked at the pressure it exerts, that it's perpendicular, and then we went on to understand quite a few things about how pressure varies with depth and all of that, right? Exposure to gravity, and how a force at one end it gets distributed all over the place, the pressure remains the same, and so on and so forth, right? So the pressure gets distributed, and at the same height the pressure is the same. Quite a few things. Then we looked at buoyant force and get an expression for that, and using that we saw how few of the devices that we use day in and day out, they work, the basic principles. And now we are moving on to the same fluid moving. Okay, so now you can look at the screen. So we have fluids moving, aka known as fluid dynamic. That's the name given to such scenarios. So two things can happen. Again, a bit of classification again over here. You can either see a laminar flow or a turbulent flow. Let me actually show you what is laminar. That will make it clear. So what we are looking at is laminar flow. Okay, so please, this naming is wrong actually. Anyways, what we're looking at is laminar flow versus turbulent flow. I'll start with turbulent flow. So just have a look at it. See the yellow dots. What's happening? How are they moving? Can we predict how they are moving? No, right? It's random. Look at the laminar flow. So laminar flow, yes, they are straight and they have a definite, you can look at it and you are looking at set of particles which are moving in a steady and particular direction, manner, and all of that. It need not be a straight motion like what I just showed. This is an extreme case. So let me explain this now. See, a fluid, pretty much everything and anything is made up of bunch of particles, right? Now, you can have these particles moving in this manner, in a steady pace and along a curve, and all of that is okay. This is an example of, right? It need not be straight. Again, what I'm trying to show is it need not be straight. This is an example of laminar flow. One of the possibilities. Not exactly, but you guys got it, right? What I mean over here is they have a definite way of moving across and it looks stationary, So what I want you to do is, okay, I want you guys to go to the web, search for laminar flow. Actually, even I could have done that. Anyways, I didn't do it. So laminar flow has to do with, actually I still can do it, but anyways, I started off. So if I have a very thin pipe, which we have actually connected to our filter and all of that. So when I fill the water, okay guys, it looks something like this, it looks, you can predict the path and it looks stationary. It looks like a photo, honestly. Even if I take a photo and show it to you guys, it looks like a laminar flow, you can't differentiate between laminar flow and the photo basically. Okay, so laminar flow has to do with particles moving in a definite manner per se. While you're turbulent, the word turbulent is there. So pretty much this is an example of turbulent. So you have particles moving around everywhere and so on and so forth. That is an example of turbulent flow. And by the way, this is just an overview. We'll be going in detail with all of this. Now, when will a stream, the same water or a smoke, when will it move as a laminar flow? When will it move as a turbulent flow? Well, There are a lot of factors, but main factor is that viscosity. So viscosity is nothing but the degree of internal friction in a fluid. Okay, so basically if the friction increases, viscosity is more. So because of viscosity, friction is more, or actually it's one and the same. So if the viscosity is more in a fluid, then it is if the friction is more in a fluid, then it's said to be more viscous per se. So there are a lot of factors that it depends on. We'll be learning about all of this. I don't want to dive into it as of now. Just an overview. So if you have a streamlined flow, if we happen to use a more viscous material, it can turn out to be turbulent. If it's non-sticky or less sticky, with viscous, if we have more viscous in the same liquid per se, right? Not the same liquid, but somehow if you are able to increase the viscosity, it becomes more sticky. And the velocity profile from being straight to curved is what we'll get to see. So what does this velocity profile and all of this mean? And everything that you're seeing in this video, we'll be understanding in detail. So viscosity is the gooiness of things. It's the stickiness of things in some sense. For example, honey is more viscous than water. The internal friction in honey is more than water. So that's why it takes a lot more time to fall basically. Okay. So that's a brief overview of what we're learning in this section. There's one word that you should know. So gradient or slope. How steep a line is the gradient, if not the slope. We have to understand the word velocity gradient. I think I showed it to you guys. Where is it? Right, velocity profile. Okay. Yeah, velocity gradient. Viscosity is it depends on velocity gradient. So what is this velocity gradient? I didn't want to make a separate video because it's a small topic. So I just wanted to finish over here. See, velocity gradient is nothing but rate of change of velocity of a propagation with distance normal to the direction of flow. So let me explain this way actually. Okay. Let me put it across you guys with this. So this is a non-zero velocity flow with a non-zero velocity gradient. So what does it actually mean? So let me make use of it. So we saw this set of particles moving from left to right. So the direction of flow is from left to right. So that's your direction of flow. Okay. Say let's consider particle A and another particle B. And say the difference between their paths per se is said to be 1 meter. So this has 2 meter per second speed and this has say 8 meter per second speed. Okay. Now the velocity gradient or difference in the velocity between particles which are 1 meter apart is 6 meter per second. Is that correct? So velocity gradient between or velocity gradient for this particular scenario is nothing but the difference in the velocity of particles which are perpendicular to the direction of flow. So this is a perpendicular, right? This is perpendicular to the direction of flow, right? It can be either up or down, but still perpendicular. Okay. So along the perpendicular line, you should take two particles. Look at the distance between their stream, between their layers per se, and take the ratio. So in this case, the velocity difference is 6 and the distance between them is 1. And the velocity gradient is 6 per second. Okay, so that's how you figure out the velocity gradient. So what does it actually mean? See, basically, when we said to have a non-zero velocity gradient, means the particles in different layers will have different speed. Okay, as in when you move up, either it will increase or decrease. So that's the whole funda. It can also, of course, decrease. It need not just increase. Okay, so I'll show you scenario wherein it is increasing and decreasing. So this is something that we'll get to see as well. So we have some viscous liquid over here. So you'll see something like this. Okay, not that. Okay, not that again. Let me start over here and maybe something like this. So we have the center particle with lot more velocity than the ones which are behind it. Sorry, not behind it, above and below it. So this is the end of the surface per se, or well, this is a container and this is a fluid. So you can see that in this space, the velocity gradient is increasing and then it's decreasing. Okay. So velocity gradient is nothing but if someone tells velocity gradient, velocity, gradient means slope. So you can see that there is a slope, right? All the particles at the start, they started at the same point because they have different speed, right? The top one is moving at a highest speed possible and the bottom one is with the lowest speed, and you can see they're covering distance, unequal distance and equal interval of time. And so that it creates a slope kind of scenario, right? There's a gradient, there's a slope, and as a result what we're looking at is a velocity gradient of 6 per second. So every second a particle which is 1 meter above or below has a difference of 6 units. I hope you guys understood that. So it's a bit of math actually. Just try to make sense out of it. Take a second, try to make sense out of it. I have a particle. I have one more particle which is 1 meter perpendicular to the direction of flow. If I look at the speed in that stream, it will be 6 meter per second faster or slower. Okay guys, so that's the funda. So yeah, I think that's enough for this video. Let's go back and have a look. Left to you guys, what you want to write it over here is just an overview. This you guys can write.